Namaste everyone. We have been discussing about electric field and charges problems, and we have completed 20 problems. Now we will discuss the remaining problems, and here is the problem number 21. Okay, so hope you are doing well. Let us start 21st problem. So here goes the 21st one. Today we have a little bit more display and I can use enough space for solving the problems. So here is the easiest problem. So these are all brushing up problems. 4 charges of magnitude plus 1 nanocoulomb, minus 1 nanocoulomb and plus 3 nanocoulomb and minus 5 are placed at the corners ABCD of a square ABCD of side 6 meters. The potential at the center of the square is. So just potential is a scalar quantity. You need not worry about the directions and all. Simply go on adding as if you add scalars, but take care of positive and negative signs. So if you take a square like this, then, and if you keep the charges at the 4 corners, what are the charges? 1 nanocoulomb, minus 4 nanocoulomb, and plus 3 nanocoulomb, and finally minus 5 nanocoulomb. These charges are kept at the corners A, B, C, D, A, B, C, D. This is a very simple problem actually, but just we can refresh about the potential formula. Side is 6 meters, so if this is 6, then this is the whole AC is root 2 into 6 meters. And what about AO from the center? Of course, you are finding the potential at the center. So AO, and every distance from every corner to the center will be AO is equal to, hope you can see this, AO is equal to root 2 6 by 2, that is 3 root 2 meters, right? So this is the distance of the center from the charge. So what is the potential at the center now? The net potential at the center, VO, is equal to 1 by 4 pi epsilon naught charge A, QA by AO plus QB by BO plus QC by CO plus QD divided by DO. So all these distances are equal, and AO, DO, everything is 3 root 2. So AO is equal to 3 root 2. So what will be the net potential at the center now? If you want to find it out, then it will be equal to V naught is equal to 9 into 10 to the power 9 into I think you can write everything, every nano outside, because every nano will come here. So it is 10 to the power minus 9, and what will remain? And every AO, BO, CO that will come in, come outside. AO, BO, CO, DO, everything will come common by 3 root 2. And inside the bracket, QA plus QB plus QC plus QT. That is the only thing which is remaining. So what is the answer for that? QA plus QB plus QC plus QD. And that will be 1 minus 4 plus 3 minus 5. Minus 9 and plus 4. Minus 9 and plus 4. Minus 9 and plus 4 is minus 5, right? It is 4 minus 9 minus 5 nanocoulomb. Nano has been already taken outside. So what is remaining here? V naught is equal to, it will be 3 3s are, right? 3 3s are, and this is minus 15 by root 2. So this here you have 7.5 everywhere. Of course 15 into root 2, that is not possible. So 15 by root 2. So you write it as minus 7.5 into 2 divided by root 2, because you have these two answers. That is not possible. So this is root 2 into root 2. So finally it is minus 7.5 root 2, correct? That is this answer. So option third one. So just simply applying the potential formula and finding the net potential at the center. So we will move on to the next one. Very easy problem. Next problem goes like this. A spherical conductor of radius r placed in air is given a charge q. Then the potential at a point inside the conductor at a distance r by 2 from the center. So you have to, you should know the formula of for electric potential. Electric potential is 1 by 4 pi epsilon naught q by r. 1 by 4 pi epsilon naught q by distance, okay, q by r. Now it is r by 2 from the center. You know, inside a spherical conductor, potential is same everywhere as if it is on the surface. So even if you are moving inside to a distance of r by 2, you have to put the potential as it is on r, because potential here, here, everywhere is same. So it is just radius, you have to put nothing else. So this is r. Even though the distance is r by 2, it is simply r. So what is the answer? This one, right? It is 1 by 4 pi epsilon naught q by r. Don't be under the impression that you have to put the distance once you go inside the spherical conductor. Once you go inside, the potential is same as on the surface. So easy question. First one, answer option 1. Okay. Yeah. Two concentric thin metallic spheres of radii r1 and r2, r1 greater than r2, carry charges plus q1 and plus q2 respectively. Then the potential at the common center will be, okay, very easy. It is the potential due to both the spheres. So we have one sphere of radius r1 greater, so this is r2, and another concentric sphere of radius r2. One is charged to q1, sorry, this is r1 greater, it is given r1 greater than r2. This is q1 and this is q2. Okay. Now what is the common potential at the center? Very common. It is question. V is equal to net potential at the center. Both the charges are positive. 1 by 4 pi epsilon naught is common in both. There is no problem with 1 by 4 pi epsilon naught. So what is uncommon? Q1 by r1. Potential at the center of this sphere due to its charge q1 is as on the surface, right? Q1 by r1. What is the potential due to this here? As on the surface. Q2 by R2. So both will produce a potential at the center which is same as on the surface, that gets added. So that is the net potential. Of course the answer is 1 by 4 pi epsilon naught times it is given Q1 by R1 plus Q2 by R2. It is not this one. Oh, this is what marked last time. This one. This is Q1 by R1 plus Q2 by R2. It is separate. That cannot be the answer. If you take the common denominator, it will only look like this. So the third option is the correct one. Okay, now suppose you are asked to find out the potential. Okay, this is okay. Potential at a distance x from here. Say this is x. Now this point is a point, we will analyze it. Even though this problem is over, we will analyze it. This point is a point which is inside the spherical conductor 1. It is inside this one, but outside this one. For this you have to put the distance. For this one you have to put the radius. So what is the potential at that point? Potential here, V is equal to, or V of x, V at x is equal to 1 by 4 pi epsilon naught Q1 by R1 itself, because radius itself, it is inside potential, whereas here it is outside, Q2 by x. This is what you have to do, right? Suppose it is asked to find out what is the potential here. If you are asked to find out the potential on the surface of the inner sphere, then potential, I will name this point as some y. Then potential at y is 1 by 4 pi epsilon naught. Hope you can see this. 1 by 4 pi epsilon naught Q1 divided by R1, because for this sphere it is the inside point. For this sphere it is on the surface, plus Q2 by R2. So like this way it keeps on going. Only all these things are built only under the platform that potential outside a spherical conductor varies with distance. It depends on distance. Potential inside doesn't depend on the distance. It depends only on the size. So that means radius. Whatever be the point inside, you have to put radius here in the form of distance. That's the only thing. Okay, shall we move forward? So now the option is third one. Okay, next question. As I rub, you can read the question. Of course. Yeah, 24. So before going to 24, you should remember, rebrush all these geometric progression. If you have a geometric progression like this, then the common ratio, first term, I1 minus r, all these things I need not teach you. You have enough knowledge to teach me because you are good in mathematics. Right, now the problem goes like this. 24. An infinite number of charges, each equal to 0.25 microcoulomb, are placed along the x-axis at x equal to 1, x equal to 2, x equal to 4, x equal to 8. You see the distances 1, 2, 4, 8 and so on. The distances are in meters. The electric potential at x equal to 0 due to all these sets of charges is. Okay, so you need some mathematical background, that's all. And physics involved is the same. Potential due to a point charge is, potential due to any point charge or a spherical conductor at a distance r is 1 by 4 pi epsilon naught q by r. Work done in taking the charge. Now an infinite number of charges are kept, right? How they are kept? They are kept in such a way that at 0 you don't have any charge. At x equal to 1 you have 0.25 microcoulomb. So at 1 you have 0.25 microcoulomb. Okay, 0.25 microcoulomb, and then you have at 2, x equal to 2, you have another 0.25 microcoulomb. So here you have, then you have 4, here you have, then 5, 6, 7, 8, here you have. So you have the charges at 1, 2, 4, then 8. What is the net potential here? Net potential, I will call this as origin, at O is equal to, potential at O is 1 by 4 pi epsilon naught, that is common, and nano is, micro is common, micro, all the charges are micros, so I can take 10 to the power minus 6 for each one. Then 0.25 is also common, 0.25, 0.25, 0.25, 0.25, I can take it outside. 0.25 is common. Then what is remaining? Distance 1 by 1 plus 1 by 2, 0.25 micro by 1, 0.25 micro by 2, 1 by 4 plus 1 by 8 plus so on. So this is what you get, right? Right. Now potential at O is equal to, this can be written as 9 into 10 to the power 9 into 10 to the power minus 6. 1 by 4 pi epsilon naught is 9 into 10 to the power 9. Okay, what else? This can be written as 1 by 4 into this progression 1 plus 1 by 2 plus 1 by 2 square plus 1 by 2 cube plus so on. Okay, then potential at O is equal to, and this will be 9 by 4 into 10 to the power 3. What else here? This is 1 by 2 is common ratio. First 1 divided by first term minus common ratio, right? That comes to half. 2 comes to the numerator. 2 2s are 2 4.5s are. So 4.5 into 10 to the power 3 volt. Is it so? Did we go wrong anywhere? No, isn't it? So x equal to 1, 2, 4, 8. Charges are 0.25 microcoulombs, common, 1 by 4 pi epsilon, 9 into 10 to the power 9. 0.25 I have taken it as 1 by 4. This is 9 by 4 into 10 to the power 3, correct. Micro and 9 into 10 to the power 9, yes. Then 1 by 1 minus 2, 2 common, 2s are 4.5 into 10 to the power 3, 4,500 volt. Is this one? This is the correct answer, 4,500 volt. Okay, so this we have some other problems also of this type. Suppose if the charges are placed, your electric potential at the point x equal to 0. If an infinite number of charges is equal to 1 nanocoulomb are placed at x equal to 1, x equal to 2, x equal to 4, x equal to 8, I think you can work it out, right? So suddenly I will I have to get the answer abruptly now. So without any introduction or anything, I can directly solve the problem here. Potential at the origin is equal to 9 into 10 to the power 9. Then what else? Each nanocoulomb 10 to the power minus 9, and each distance 1 by 2 plus 1 plus 1 by 2, same, so that comes to 2, right? 1 by 1 minus 2, common ratio. So is it potential is equal to 18 volt? Yes, this answer. Second one. See how the experiences teach you, right? You can skip off the steps because this becomes 1 by 1 minus 2 because common ratio is half. Okay, 26. Now you are asked to find out electric potential, a small difference at the point x equals 0 due to this set of charges if alternate charges have opposite sign. Yeah, it is interesting now. All are 1 nanocoulomb charges, but alternate charges are of opposite sign. So what you will do? Okay, potential at center 1 by 4 pi epsilon naught, 1 nano, every 1 nano, 1 nano, 1 nano, 1 nano. Alternate charges are of opposite signs. So first one is 1 by 1, next is 1 by 2 minus 1 by 4 minus 1 by 8 plus so on, right? It should be like this. First charge positive, next charge negative. Of course, common values are taken. 1 nano is taken outside, 1 nanocoulomb is taken outside, but the negative positive signs are retained inside. Plus minus plus minus plus minus like this. Potential at the center is 9 into, this is 10 to the power 0, 1. 1 minus half and all, you can write it as in the ratio, common ratio 1 by 2. 1 minus or plus 1 by 2 to the power, minus 2 to the power 1, right, plus 1 by 2 to the power minus 2 to the power 2 plus 1 by minus 2 to the power 3 plus, see, wherever you have cubes to the power 5, odd powers, you minus sign retains. Wherever you have even powers, square to the power 4 to the power 8, and that becomes plus. So this is 1 by 2, 1 by minus 2 whole square, 1 by 4, 1 by minus 2 whole cube. So this can be written as, so 1 by minus 2 whole cube is the common factor, 1 by minus 2 is the common ratio, right? So I can write it as potential at the center as 9 into, yes, first term minus common ratio minus 1 by 2. Minus 1 by 2 is the common ratio. So 1 plus 1 by 2, 3 by 2. 2 goes to the numerator and 3 remains in the denominator. It is 3 by 2, 1 plus half. By 2 goes to the numerator. 3 3s are, so 6 volt. Here is the answer. So very easy now. Now if electric field is asked, that is the next problem, 27th one. We'll move on to the 27th problem. Electric field is asked. Yeah, this is 25th. Yeah. An infinite number of charges, each equal to 1 nanocoulomb, are placed along the x-axis, 1, 2, 4, 8 and so on. Distances are in meters. The electric field at x equal to 0. Electric field at x equal to 0. Right. What you will do now? How to find out the electric field at x equal to 0? Yeah. Charges must be placed 0, 1, 2, 4, 2 here and 4 here, 5, 6, 7, 8 like this. Now if you place charges of 1 nanocoulomb or something else as 1 nanocoulomb, 1 nanocoulomb, 1 nanocoulomb, 1 nanocoulomb, 1 nanocoulomb, if you place a test charge here, all of them will repel them, right? The unit positive charge is repelled by all the charges like this. So you need not bother about the direction. Direction of all the electric fields are same. So you can keep on adding it. So what is the net electric field here at the center? E is equal to 1 by 4 pi epsilon naught, and all the charges are positive now. If the alternate charges are of opposite sign, yes, electric field, if the alternate charges are of opposite sign. So Q by R squared, Q by R squared, Q by R squared. R squared keeps on changing. I think you can follow it. Q, 1 into 10 to the power minus 9, common, by R squared, 1 square, and the second charge is negative, 1 by 2 square, and plus 1 by 3 square, because electric field formula is 1 by 4 pi epsilon naught Q by R square, and plus 1 by 4 square, no 3, right? It is 4 square, and next one is even, it is negative, minus 8 square. Electric field E is equal to 1 by 4 pi epsilon naught 10 to, you can write it as 1. 9 into 10 to the power minus 9, 9 into 10 to the power 9, 10 to the power minus 9. 9 into 1 minus 1 by 4 plus 1 by 16 minus 1 by 64 plus so on. Now how can you take it? You can write it in the terms of 1 by 4 to the power, but 1 by minus 4 to the power, because you have to have, wherever there is odd power, you should get minus, even power plus. So E is equal to 9 into 1 minus 1 plus minus 4 to the power 1, 1 minus 4 to the power 2, 1 minus 4 to the power 3 plus so on. So this becomes plus, this becomes minus. So E is equal to 9 into 1 by 1 first term minus common ratio minus 1 by 4. What is this? 1 plus 1 by 4. It is 5 by 4, correct? 4s are 1s are. 5 by 4, 4 by 5, 9 into 4 by 5. Correct? This is 5 by 4, 4 4s are 4 1s, 1 4s are 4, yes 5. This is 36 by 5. That is equal to 7s are and 2, 7.2 volt per meter. Here itself is the answer. That is the answer, right? So again another simple problem. So all the thing is you should know that infinite series addition, geometric progression. Okay, 28. Yeah. Right. The electric field at a point x equal to a set of charges. Yes. 1 nanocoulomb, 1 to 4. Only the difference here is you have all the charges positive, infinite number of charges. Positive charges means this is all positive. That is the only difference you have to go for. And if this is all for positive, this is a plus 4 and this is as in sum up to infinity 1 by 1 minus common difference. 1 minus 1 by 4 is 3 by 4, correct? It is 3 by 4 and this will be 3 and this is 12 volt, correct? This one answer for this question. This will be 12 volt then. That's all. You can do it easily, right? Hope you can do that. Okay. If at all you have problem, you have not understood, because there is no question of spending time in the same type of problem. You just message it to me and I will answer it, right? Okay, moving on to the 29th problem. Gauss law. This problem is based on the Gauss law. Right. Now, you know the Gauss law. Flux through any closed surface is 1 by epsilon naught times the total charge enclosed within the surface. Flux through any closed surface is 1 by epsilon naught times the total charge within the surface. Of course, this Q must go to the numerator. 1 by epsilon naught times the charge enclosed. Now, that means the Gaussian surface doesn't come into picture here. That means what type of surface you are enclosing for using enclosing the charge, that doesn't come into picture. That means flux through, suppose you have a charge Q, flux through a spherical Gaussian surface, the number of electric field lines passing normally through this surface, and if this charge is enclosed by a cubical box like this, or whether that charge is enclosed by a cylinder like this, whatever it is, flux is same. Whether you are enclosing a single charge by a smaller sphere or a larger sphere or a cube or whatever it is, flux through all of them are same. If you enclose a bulb within a sphere, if you enclose a bulb inside a same bulb inside a cubical box, the energy coming out will be definitely the same. The rays of light coming out will be definitely same. So flux is independent of the shape and size, one thing. But it should be enclosed, that's all. You shouldn't place the charge at one corner of the closed surface. You should enclose it. So flux through any enclosed surface is 1 by epsilon naught times the total charge. Now, that is what the answer you need here. There's cube and a sphere enclose the same charge. Their volumes are in the ratio 1:2. So cube may be smaller and the sphere may be larger. But what is the flux through them? It should be 1:1, no doubt in this. Flux through any closed surface should be same, irrespective of its size and shape. Okay, 30. Yeah, if the electric flux entering and leaving an enclosed surface respectively are phi1 and phi2, the electric charge inside the surface will be. So if a surface, if an electric field enters the surface and leaves the surface, entering is phi1, leaving is phi2. Always entering flux is taken as negative and leaving flux is taken as positive. That is a usual notation. Entering flux is taken negative. Why it is so? Suppose you have an electric field like this. Say you have a positively charged capacitor plate here, negatively charged capacitor plate here. Then if the electric field lines are like this, I will place a cylinder in the electric field, okay? A cylindrical surface in the electric field like this. This cylindrical surface is not enclosing any charge. There is no charge inside the cylindrical surface. Now the electric field lines are passing through the cylinder. Okay. Now how do they pass? And always flux through any open surface, not closed surface, is E delta S cos theta, right? Where E and delta S are vector quantities, their dot product gives the flux. Electric field dot the surface area. How come surface area vector? The normal to the surface area is taken as vector. That means, which normal? If you have a surface area like this, you can assume a normal like this, or you can assume a normal like this way also. There are two normals possible. Outward moving normal is taken. So it is the dot product of electric field and the area. The normal to the area gives the direction. Outward moving normal. What do you mean by outward moving normal? For example, here, this is the outward moving normal. This is the outward moving normal to the surface. Now if you write the flux, suppose the area of this is A, area of this is A, the two circular faces of the cylinder, then outward moving normal is here like this, outward moving normal is like this. This is the direction of electric field, right? Now you see, what is flux through this surface? Flux through this surface, phi 1, entering. Electric field is entering. But outward moving normal is like this. E delta S cos 180. Why 180? Because electric field is coming out and electric field is moving in and the normal is coming out, so they are in opposite direction. Cos 180, that becomes minus E delta S. Cos 180 is minus 1. What about here? The electric field is moving out, outward moving normal is coming out. They are parallel to each other and directed in the same direction. Theta is 0. So what is the flux through this circular face? Is E delta S cos 0, that is equal to E delta S. Now you see here minus E delta S plus E delta S, and so outward moving electric field is taken positive. Inward moving electric field is taken negative, only for the reason that the outward for incoming electric field, normal will be coming out. For the outgoing electric field, normal will also be going out, because we are always taking outward moving normal. So normally this is phi 1 minus and this is phi 2 plus. So they are asking you, entering flux is phi 1, leaving flux is phi 2. So apply this. Net flux is nothing but phi 2 minus phi 1, because plus phi 2 minus phi 1, that is equal to 1 by epsilon naught times the charge enclosed. Their question is, what is the electric charge inside the surface? Of course, even if you take a charge inside, and if there are, so their question is actually not this one. Their question is like this. Suppose you have a surface like this, closed surface like this. This is plus Q1 and minus Q2. There are two charges inside, plus Q1 and minus Q2. Plus Q1 will have outward moving electric field lines. What about minus Q2? Incoming electric field lines like this. What is the net charge? That is what is their question. Correct? It is like this. So, and our normal is always outward moving normal, like this, like this, like this. So that is outward moving normal. So with respect to these outward moving normal, this is in the same direction, cos 0. This is in the opposite direction, cos 180. So what is the net flux? Phi 2 minus phi 1. Because phi 2 is entering and leaving, right? Phi 2 is plus. Entering, it is minus 1. So what is Q? Epsilon naught into phi 2 minus phi 1. Correct? Fourth one? Yes. Epsilon naught into phi 2 minus phi 1. That is Q. Okay? That is this situation actually. But that was a cylinder which was taken in an electric field. So don't confuse it with one. But the way of applying flux is same. The normal is always taken as outward moving normal. Okay? Right. Shall we move on to the next one? Yes. 31. When a number of identical drops of water, drops of any liquid combine together form a single drop, what are the changes occurring in the single drop? That is the question now. Number of drops combine together to form a single drop. Yes. Now, Suppose there are n drops, identical drops, n drops of the liquid. They combine together to form a single drop, and each of radius r and charge q. Each drop has a charge q and radius small r. Now they combine together to form a bigger drop r of radius r. Now when you analyze this one, the drops, when they combine together, the surface area will not be n times, because the surface area of these drops do not contribute to the surface area of the larger drop. Only on the side of this drop the charges will contribute, and their surface area will be counting for the surface area of the larger drop. Whereas so surface area decreases when you have many drops like this. You calculate the surface area of each drop and add it. That will not be the surface area of the bigger drop. It will be less. Total area of all these will be more. So, but volume will be n times more. So volume of larger drop is n times the volume of smaller drop. If you take each volume, then this will be n times. That is sure. So what is the volume of larger drop? 4 by 3 pi capital R cube is equal to 4 by 3 pi small r cube. Correct? 4 by 3 pi gets cancelled. So r cube is equal to n r cube. N times, yes. N times the volume of the smaller drop. R cube, r is equal to cube root of n small r. First conclusion. So when n drops combine together to form a bigger drop, the radius of the larger drop is equal to cube root of n times the radius of smaller drop. That is a very simple conclusion. Now we will go to different values. For example, what is the charge of the larger drop? Of course, charges of all these drops will come outside, because you know that charges always reside on the outer surface of a conductor. Suppose this is a conducting medium, the charges will come to the outside. So charge of the larger drop is n times the charge of the smaller drop. There is no doubt, right? Charge of the larger drop is n times the charge of the smaller drop. Radius of the larger drop is cube root of n times the radius of the smaller drop. Now we will see surface charge density. How did you get surface charge density of larger drop is cube root of n times surface charge density of the smaller drop? Very simple. You know that surface charge density sigma is equal to charge by area, q by r square, right, for any sphere. So surface charge density of the smaller drop is small charge by small, okay, this is proportional to, okay, or we will write the formula itself. Charge by area, charge by smaller drop height, right, smaller charge divided by 4 pi r square. What about larger drop? Full charge divided by full radius. But this can be written as surface charge density of larger drop is n times q, right, because the charge of the bigger drop is n times the charge of each smaller drop. Nq divided by 4 pi capital R squared. Capital R is cube root of n times small r whole squared. Now divide this, sigma of larger drop, sigma of smaller drop. I am doing this for the reason that once you come to know about this, suppose you forget it in the exam, you can get the answer. So better not to by heart the formulas. Know the way in which it is got. So sigma L by sigma S is equal to. So in sigma L you have n by 4 pi small r squared. In sigma S you have q by 4 pi r squared. Sorry, q by 4 pi r squared, q by 4 pi r squared. So here the thing which is remaining is n by n to the power 2 by 3, because n to the power 1 by 3 whole square, n to the power 2 by 3. So what is this one? This is equal to 1 minus 2 by 3. It is 1 by 3. N to the power 1 by 3. The surface density of larger drop is cube root of n times the surface density of smaller drop. Is it so? Yes. What about capacitance of larger drop and capacitance? I'll leave this to you, right? Because potential, you know, charge by radius. Charge by radius, you can do that. Capacitance, you know, capacitance of a spherical conductor is 4 pi epsilon naught r. It depends on the radius. Radius is cube root of n times smaller drop. Then capacitance is also cube root of n times smaller drop. Potential, I'll leave it to you, okay? So these are the formulas. Now once you know this theory, nothing is involved in the problem. That's why I included only one problem. N identical mercury drops charged to coalesce to form a, of course, same potential V, coalesce to form a single drop. The potential of the new drop is n to the power 2 by 3. Because, okay, we will do that now. we just left it in the previous discussion. We'll do it now. Yeah, what is the potential of smaller drop? 1 by 4 pi epsilon naught, its q by its radius. What is the potential of larger drop? 1 by 4 pi epsilon naught, its q by its radius, which is also equal to 1 by 4 pi epsilon naught, its q, which is n times the charge of each drop, smaller drop, divided by cube root of n r, because capital R is cube root of n of small r. What is this? Potential of larger drop by potential of smaller drop. Everything what is here, it is here now. 1 by 4 pi epsilon naught q divided by r. Remaining is n by n cube root of n. 1 minus 1 by 3, n to the power 2 by 3. Bring this here. Potential of larger drop is n to the power 2 by 3 times potential of smaller drop. That's all. Okay. Then 32nd problem. Yeah, this part we will do it later. For the timing, I'll stop it today. We will move on with a few more problems, because this needs a little bit one package of class. I will do that in the later stage. Today I couldn't get more amount of class, but I will speed up in the next few days, because I am recording the videos. Now I don't get enough time to do all those things. So I am clubbing everything, and then we will start full-fledged class. So thank you for watching this class. Keep on working the problems. 10 more problems you have with your sheet. That is PDF is given. So keep on working. Thank you for watching. Thank you.